Good morning, everyone. It's my pleasure to introduce Dr. Sarbani Basu, who is the William K. Lehman Jr. Professor of Astronomy and also the Chair of Astronomy at Yale. Dr. Basu received her training in India and subsequently worked in the UK and Denmark before arriving in the US to study at the Institute of Advanced Study at Princeton. She's been a faculty member since 2000, and she is a member of the board of directors of the Association and Universities of Research in Astronomy, which is a consortium of educational and nonprofit institutions that operates in the US. Dr. Basu's specialization is the sun, and she's going to talk about how she uses the sun to tell us a little bit of insights of what's going on. Her past research was devoted to the details and structure and dynamics of the sun, and our current research focuses on two separate topics. The first is the study of the variations of the sun over large timescales. And then her second area of focus is to understand stars, distant stars, and exoplanet hosts, to determine their structure and age as well. So without further ado, I hope you guys enjoy an illuminating talk, and I'll give it over to Dr. Basu.
Thank you very much, Zach. So what I would like to talk about today is not something we normally dwell on, which is how the sun affects us. And I'm not talking about the stuff that we all know, that the sun is why we're here, the sunlight gives us energy, life wouldn't have been possible without the sun, but a bit more about its malevolent effects, particularly its effects on technology, what can have, and I'll also talk a bit about what we're trying to do about it. So the image here on the background actually shows you a gigantic loop of gas just about to explode from the surface of the sun. And how big this is, you can understand by this little tiny little Earth sitting here. So we're talking about huge explosions, okay? So let's go to the beginning. So the sun is our nearest star. So if anybody asks, it tells you that the nearest star is Proxima Centauri, don't believe them. The nearest star is in our background. And it happens to be a sort of run-of-the-mill, not very heavy, middle-aged star. So it has a radius which is about 110 times the radius of the Earth. Its mass is 2 billion tons. It's mainly hydrogen and helium and a little bit of everything else. And its surface temperature is roughly 6,000 Kelvin or 10,000 Fahrenheit. But that's just the surface. The region of the sun where energy is being produced by nuclear reactions is more at 15 million Kelvin, which is something, if I've done my conversion correctly, something like 27 million Fahrenheit. And the sun is about 4.5 billion years old. So why do we care? The sun affects everything on Earth. We live in the sun's backyard. Yes, it's responsible for life on Earth, and we depend on it directly or indirectly for energy. And of course, it also affects climate. However, it's not so much the sun as it's not the usual effects of the sun that bother us. It's more the fact that the sun is a magnetic object which has a magnetic cycle. The magnetic field of the sun rises and falls and rises and falls, and that is what affects Earth. So geomagnetic storms, these are storms of the Earth's, these are disturbances to the Earth's magnetic field. These are caused by solar flares, I misspelled flares, and mass ejections, and these harm technology, and that is a big issue, okay? So what happens? How can the sun harm us? The sun emits tons of material, and what you'll see is a movie of one of the mass ejections from the sun. This was from 2003, seen by an instrument called LASCO, on SOHO. LASCO is a coronagraph. So it basically is a camera that can look at the outer layers of the sun. It blocks the sun. So this white circle shows you where the sun is, and this red band is where you're blocking the sunlight because it's very bright. You want to see the faintest structure beyond that. So what happens? You will see there. You see there's a huge amount of mass that is released by the sun on that particular day. So the thing is, the Earth's magnetic field does provide some shielding. So this is a sort of schematic image of what the magnetic field around the Earth looks like. You see the white lines? This is what the magnetic field would have been had the Earth not continuously being bombarded by the solar wind. What the solar wind does, because solar wind is basically particles from the sun, they carry charge, they carry magnetic fields, it squashes the side that is towards the sun and extends the side that is on the far side of the sun. And that is shown by the brown lines, okay? And charged particles cannot cross these lines. They are forced to move along the lines, and so they only affect the Earth near the poles. This is the normal situation, but things can become quite different when you have a violent mass event. So what happens? This is a nice visualization from NASA. You will see a blob of material being ejected. This is just a visualization. This is not a real thing. A blob of material being ejected, then affecting the magnetic field of the Earth, and you'll see the response of the geomagnetic field when this mass affects the Earth. So let's try. So there's the sun. There's a blob of material traveling through space, hitting the Earth's geomagnetic field, squashing it, changing its configuration, and producing fantastic aurorae at the poles. Okay. Depending on the energy in these storms, the aurora can be seen quite far south in the northern hemisphere and quite far north in the southern hemisphere. So let's look at it again. So there's the mass being ejected, and there is the geomagnetic effect of it. Now, the thing is, there's very little effect of these on life directly, because most of the particles that they reach in the polar regions where there is very little life. However, it's not life we are bothered about, it's technology. So the first indication of the effects of such a solar storm on society was the so-called Carrington event of 1859. Telegraph operators reported sparks from the equipment. Some were bad enough to set fires. And they discovered that the telegraph lines had so much energy that you could send messages without connecting them to a battery. Okay. Now, telegraphs were the internet of those days, the technological marvel of those days. And you have to keep that in mind. That's one of the reasons why the telegraphs were affected. There was basically nothing else. And ice core samples have since determined that the Carrington event, as we call it, because Carrington saw it and recorded it, was twice as big as any other solar storm in the last 500 years. Okay. What would happen if we had a Carrington event today and we couldn't take precautions? We would probably have trillions and trillions and trillions of dollars in damage and a disruption of society. It's satellite communication. It's And I don't just mean GPS. Remember, we use satellites for television, for radio, not so much for radio, television mainly. We use satellites even when you're swiping your credit card. You need the satellites to be active to send the signal and come back. It can overload power lines. It can disrupt communication on a large scale. So it can be extremely dangerous. Again, dangerous not to life directly, but to life through technology. So there was, in fact, a huge blackout in 1989. Remember, 1989 is pre-internet days, okay? Due to a solar event that occurred on March 10 of that year, the effects weren't felt on Earth until March 13. About 2 a.m. of that day, the power grid in northern Quebec, particularly these areas that are shown in gray, the electric lines were basically overloaded and they tripped. Now, this image, you see these deep hashed region, that is where you would normally see an aurora. But because of that solar storm, you could see aurora as far as Texas. And the US wasn't spared either. There were actually power events all throughout the US, though no big blackout. And there were communication satellites that recorded anomalies because high energy particles infiltrated their electronics, and there were problems all around. So that's a taste. Now, something that didn't come out till a few years ago, thanks to the Freedom of Information Act, that there was actually a danger of a nuclear war in May 1967. A solar storm, which affected mainly the polar regions, as usual, it jammed the US's radar systems in the north. And it was at first thought that that was the Soviet Union jamming the radar signals in preparation for an attack. In the US, attack aircraft had been manned and set ready. However, fortunately for all of us, the US by then had a nascent program. It wasn't a particularly old or a particularly distinguished program at that time. Program to actually study the effects of solar storms, and scientists could, fortunately, convince the powers that be in Air Force that this is due to a storm and it's not the Soviet Union preparing an attack. Another event like that, talking about during the Vietnam War, suddenly underwater mines that had been placed by the US in some of the Vietnam harbors started exploding. These mines were supposed to be triggered when ships passed, unauthorized ships passed, and changed the magnetic field configuration because ships have a lot of metal. But even without those bombs started exploding. And that was because of all the extra magnetic field that was, or the magnetic field of the Earth. The configuration changed because of magnetic particles from the sun reaching the Earth. Of course, the effects are not always malevolent. They do produce beautiful aurorae, but you can see aurora even without a storm. So, yeah, we don't like storms. The problem here is that we cannot really predict these events. We do not understand how the energy is transported to those particular regions of the sun which explode. NASA has been funding studies for a couple of decades, at least, if not more. There's a program in NASA called Living with a Star that deals with trying to understand and predict these events, but we're not very good at it. actually, we are horrible at it. So that's a problem. Now, let's go back a bit to the basics. So the sun is a magnetic object, like the Earth, it would, or like a simple bar magnet. You would see, magnetic field lines going from the North Pole to the South Pole, except that on the sun, you get these intensely magnetic features. We call them sunspots because they appear as dark spots on the sun. Okay. These are concentrated magnetic features. Now, I just love showing this image. It's nothing to do with the talk, but this is the most detailed sunspot image taken to date. This was taken by this newly constructed, not completely operational solar telescope in Hawaii called the Daniel K. Inouye Solar Telescope. It's in the summit of Haleakala. And you can see the detail of this. And the hope is by studying these, we'll be able to understand what happens in these structures, because these structures on the surface of the sun have the most highly concentrated magnetic fields. Okay, now the spots, this is a boring visible light image. But if you photograph the sun in UV light, these tiny spots look much bigger. So there's the visible light. This is UV again, but a different wavelength. So it looks much more dramatic, and it's really dramatic in X-rays. So to understand what's going on, we need to figure out how the energy from these spots on the surface of the sun is transported upwards to make the outer regions so much hotter that we can actually see them in UV and X-rays. Now, this is one of my favorite solar images. It's a composite. This is the sun taken at the image of the sun taken at the exact moment by the instruments on board the Solar Dynamics Observatory, but at different wavelengths. So this is what you would roughly see by your naked eye. This is a magnetic image. It's called a magnetograph. So you have a group of sunspots here. Now look here, there's nothing showing here, but the magnetic field image is showing structure here. And if you look at the sun in different ultraviolet wavelengths, you do see that structure appearing in ultraviolet and not invisible. So again, these are things we need to understand. It's clearly the magnetic fields are transferring energy, but how and why, we're still studying that. Now, the magnetic field of the sun increases and decreases in a cyclical manner. So 1996, and that increase and decrease is known as a solar cycle. 1996 was what we call cycle minimum. This was the start of solar cycle 23, because we started numbering them a while ago. You can see this UV image. The sun gets brighter in UV, lots of active regions. 2001, 2002 was the maximum of that cycle. Then the sun became quieter and quieter and quieter. Then the activity started increasing. This was cycle 24. The maximum was around 2015. That started decreasing. The minimum of cycle 24 was in 2020. We are currently in cycle 25. Now, you could, if you took the number of sunspots and took their average per month and plotted them as a function of time, you would see the number of sunspots increasing and decreasing and increasing and decreasing. In this figure, the colors, the blue colors are reasonably good observations. The gray are not so good, but the modern observation. So the couple of things you can see, the number of sunspots and the maximum don't vary from cycle to cycle. And the length of the cycle is not a constant. So we normally talk of an 11-year solar cycle, but 11-year is just an average. It's not really the length of a solar cycle. It's an average, okay? Now, the number of these mass ejections from the sun, okay, sorry, before we do that. Now, when the sunspots appear on the sun for a new solar cycle, they don't appear randomly. So this graph shows where sunspot appears at what time. So a new cycle starts with sunspots appearing at a high latitude on the sun. And as the sunspot progresses, the sunspots appear at low latitudes. And we call this the butterfly diagram because it looks like the wings of a butterfly. So, okay. Now, the number of coronal mass ejections, the ones we are afraid of, they increase and decrease with the solar cycle. So they show a similar increase and a similar decrease with the solar cycle. So, and if you have a very strong solar cycle, you get more of these mass ejections. If you have a weak solar cycle, you have fewer. The problem is we are hopeless at predicting how strong a cycle will be. Okay. So this graph shows predictions about how strong, what would be the maximum number of sunspots in cycle 24, which ended about a year ago. You can see the predictions range all the way from about 190 to about 40. This blue line here shows what we actually saw. So yes, there's a prediction which matched, but was that fluke or is that model really good? We will know, we hopefully will know in cycle 25, where again, NASA asked a lot of groups to predict the cycle. So this is the prediction, still has a humongous range. This is where cycle 24 lay. Now, those of you with sharp eyesight would notice that the scale has changed. That is because the scale of sunspots had been changed in the meanwhile by the solar physics community, but it's basically the same thing. So this is where we were in the last cycle. We have to wait another few years before we hit the maximum of the current cycle. And then we'll know if the model which predicted this cycle properly also predicts the cycle properly. The problem, as you can see, is solar cycles are pretty long. So an average astronomer, if you're lucky, will see 3 solar cycles in a professional lifetime. So the time scale makes predictions and everything difficult. So I'd like to step back and tell you a bit about what I do. So I don't predict solar cycles. I do not predict CMEs. What I try to do is look what is happening inside the sun to see what, I mean, after all, magnetic fields and the changing magnetic fields in the sun have to be caused by what is happening inside the sun. There is no outside agency. So what are the changes happening inside the sun that correlate with magnetic activity, which then we can study to figure out what is going on inside the sun? Once we understand what's happening inside the sun, we should be able to actually predict at least the solar cycle properly. So what I do is use the tool called helioseismology, which is nothing but the seismic study of the sun. I use solar oscillation data to make a picture of the sun. Reasonably similar to what geophysicists do for the Earth, earthquake scientists do for the Earth, but the tools are slightly different. So the sun pulsates, and this is my data. I hope you can hear the rumbling sound. This rumbling sound is a juxtaposition of many millions and millions of tones and overtones. So what we do is we take this, decompose it into the tones and overtones, and then study what happens to those tones and overtones as the solar cycle progresses, because those tones and overtones are related to the structure and dynamics of the interior of the sun. So in other words, this gives us a window inside the sun. Okay, you would ask, how do we observe sound across empty space? Sound doesn't travel in empty space. Well, we don't. What we do is look at what's happening to the surface. What you heard in the previous graph is what's known as a sonification of the data. We took the data, converted into sound so that you could get an idea of what it sounds like. We look at ripples on the surface of the sun. These ripples, think of beating a drum. Okay, if you beat the drum, the membrane moves about while causing sound. That's exactly what this is. And so these different tones and overtones penetrate to different depths of the sun, and that is how you would build up a picture of the sun. Okay. So what have we learned? Question, what does the sun look like inside? Okay, the outer 30% of the sun is a mass of boiling, churning plasma. The theory of stellar structure and evolution does predict this, but we have shown this is indeed true. The inner part is where energy is, the material doesn't move, energy is just transported through radiation. While in the outer layers, energy is transported through this bubbling, boiling gas. What seismology has done, and which is a test of how we make solar models, is given us an exact position of where this transition occurs. This is at 0.713 plus minus 0.001 solar radii. So you have to reproduce this very well to say that your model matches the sun. What else have we learned? Before we do that, this boiling structure, we see that at the surface of the sun. So this is an image of what we call granulation on the surface of the sun. It's taken by the same telescope that I showed you, the sunspot structure, the Daniel K. Inouye Solar Telescope. This is an amazing image because you can see structure as small as about 70 kilometers across. It's the most detailed image of the solar surface, which is why, of course, it made the front page of New York Times and everything. Solar physics doesn't normally do that, but it really was fantastic. Okay, what else have we learned from seismology? The temperature of the solar core is a whopping 15 million Kelvin. Now, this is actually what was expected. Just the details are slightly different, which tells us that, yes, at least for stars like the sun, a theory of how a star evolves and the structure of a star is actually quite good. Now, the interior of the star, the core of the star, it's extremely hot, but it's also extremely dense. The density is many times, I think 13 or 14 times, as high as the density of lead. So it's very dense, but because it's very hot, it's not a solid, it's a fluid, it's a plasma. So in terms of structure, our theories of structure and evolution actually turned out to be reasonably good. What surprised us was rotation. Now, the sun rotates was known the moment people saw the first sunspot. So Galileo is credited for at least claiming to see sunspots first. He didn't believe there were spots on the sun, but nevertheless. And the spots rotate, and that actually tells us how the sun rotates. But even more than that, a Jesuit priest of that time, Galileo's contemporary, Christoph Scheiner, he took meticulous observations of sunspots. And what we actually, there's a copy of this book, Rosa Ursina, I believe, in our Beinecke library. There's one in Beinecke, one in the US, one in Stanford, and I think there's one in Harvard. It's all in Latin, but the sunspot images were taken by using a pinhole camera, and they're marvelous. They're quite accurate. And what the sunspot images show, actually, that the rotation rate of the sun it's not like the Earth, where every part of the Earth rotates once every 24 hours. The equator of the sun rotates once every 25 days, but the higher latitudes rotate slower and slower and slower. The other thing that Shiner's observations showed is that the sun is tilted. Remember, the Earth is tilted at 23.5 degrees with respect to its orbit. The sun is tilted about 7 degrees. And because it's tilted, we can actually see the poles of the sun. Otherwise, we'd never be able to get any idea of what's happening to the poles. Not that we have too much of an idea, but yeah. But the real surprise that helioseismology showed us is what rotation looks like inside the sun. Okay, so this is just sunspots showing you how the sun rotates. What was expected from simple theory is that if you cut open the sun, you could imagine the sun were made up of many cylinders, concentric cylinders. Each cylinder would rotate at a different rate. So all the material on the surface of this red cylinder would rotate faster than all the material on the surface of this blue cylinder would rotate faster than the surface of this green cylinder. So if you looked at, plotted the points that had an equal rotation rate, you would get lines that are parallel to the rotation axis. This is what was expected. This is what we get. The lines of constant rotation are not parallel to the rotation axis. They have an angle. There is this sudden increase in the rotation rate just below the surface. Then the rotation rate in this part, this is the part which is the boiling, churning part of the sun. This black line demarcates that region from the quieter. So this boiling, churning part of the sun, the rotation rate is almost constant at any given latitude as you go inside. And then suddenly things become what we call a solid body rotation, meaning all the gas rotates at the same rate. None of our simulations reproduce this properly yet. So it has to do with energy distribution by turbulence in this churning ball of gas. And we don't completely understand this. We know more or less what needs to be included, but none of the simulations yet reproduce this. That is still, so there are lots of people studying this still. Then what happens to, remember I said we want to look at how the sun changes as solar activity, as the magnetic field changes. So what people did, a group, I wasn't a part of that group, did after 5 or 6 years of of data, is what they did was they found the rotation rate at each epoch that we had data for. So the space days data give you helioseismic data for 72-day chunks. And then they subtracted out the average rotation rate from the rotation rate at each epoch to see, is there any systematic behavior of what's left behind, of the deviation from the average. And what they find is they have these migrating bands. The yellow is higher than average. Red is also higher than average. These migrating yellow bands moving towards the equator as the solar sun became more and more active. And there is this high latitude band, which is going towards the pole. We now have a lot more data. We have 2 solar cycles of data, not just 6 years of data. We can see it more carefully if, instead of plotting like the way this is plotted here, what we do is just unwrap the sun and plot what happens as a function of latitude as time progresses. Okay, this is the same figure, lot more data, but plotted in a way where we can actually, measure how much things are changing and look at the pattern more carefully. So the top and the bottom figure are just are from different instruments. The top figure is from space-based instruments. This black line is when we lost contact with the satellite. It's quite scary. The lower one is a ground-based one. This white lines in the middle shows the demarcation between solar cycle 23 and solar cycle 24. And what you see is that migration pattern that you saw in the previous figure. The previous figure stopped somewhere here. Okay. That migration pattern continued and the 2 lobes joined. Sometime later, a second equatorward pattern started, which in the next cycle joined. So this is actually the beginning of cycle 24 during cycle 23 itself. So in the inner layers of the star, we can see the beginning of the next cycle years before the signature comes to the surface. Okay. So similarly, we saw the beginnings of cycle 25. Okay. And it turns out that sunspots are formed in the regions that coincide with these red bands. That's what plotted here. So which means the magnetic fields and these flows have to be intimately related. We don't know what's the chicken and what's the egg, but there has to be a feedback. And this is still being studied to figure out why are the sunspots concentrated on this equatorward path. Okay. So I'm going to end with a few thoughts. So we actually understand how the sun and other stars behave over timescales of hundreds of millions or billions of years. That's an easy problem to solve. What we cannot yet do is tell you what the sun will do, say, 10 years from now, or even a year from now. And that is where the effects of solar activity become a problem. And the other thing is, we really need to think of mitigation effects. So NASA and NOAA mainly has the Space Weather Prediction Center, where they try to predict what space weather. So space weather is basically everything that happens between the sun and Earth and even beyond. So they want to predict it and also help in mitigating it. Because since we cannot predict it yet, the idea is mitigation. So we have satellites, for example, the SOHO satellite, it's still alive, surprisingly. It was launched in 1995. That sits in between the Earth and the sun at the point where the gravitational field of the Earth and the sun exactly balance each other. So that point is 3 times as far away from the Earth as the moon is, which means if particles from a CME strike SOHO, it can tell us using light waves or radio waves that we have particles coming towards us. Light waves travel at the speed of light, so they take only 8 minutes to come from the sun to the Earth, so even smaller time from SOHO to the Earth. But particles travel with much slower speed. So we can get some advanced warning from tens of minutes to even days, which could allow you to, for example, put your satellites in a safe mode, or for astronauts to take cover, because there was an event just before Halloween of 2003 when Soho did catch a storm and gave us notice. And so what astronauts on the space station did was take cover inside the module, the Soyuz, I forget what the module called, the Russian module, which had taken them to the space station. So they had a few more layers of protection. And I remember in 2001, I was traveling from JFK to Hong Kong. It was a polar route. It was a nonstop polar route. There was a flare. So the aircraft, the route was changed because there would be too many particles coming in through the magnetic poles, which could cause radiation danger to the crew and passengers. So we do need advanced warning and figure out mitigation effects to counteract all of this. So I shall stop here. Thank you for your attention, and I'll be happy to take a few questions. No questions? Surely I wasn't. Okay. Tara.
Yeah, I'm going to apply some of my knowledge from last year's seminar with Paul Turner, where one of the things we discussed is a change in this field of science to not necessarily just look towards new technology and what is considered like Western practices, but also look into the past and indigenous practices when it comes to understanding the world around us and making it a safer place for everyone. So if we, one thing I always learned in history was a lot of ancient cultures had a much more advanced understanding of our solar system than we have now without the technology. Like in comparison, they did not have the technology we had, and they had the ability to read the solar system in really amazing ways. So is there any research into looking to the past in terms of trying to predict solar flares? Like, are there ancient, or even indigenous cultures that lived closer to the poles that did have the ability to track those things?
The records only talk of occurrences because these energetic particles won't really affect life directly, except, say, through a big radiation dose if you're close to the core. The disruptive effects, the immediate disruptive effects, is the effect on technology. We feel the effects of these because we live in a highly technological society where everything matters, even if you want to, you can't get rid of, you're dependent on computers, you're dependent on the internet, you're dependent on electricity. So that is why the mitigation efforts are not mitigation efforts to save life. It's more to save life as we know it, the technological society. So I'm not sure if I answered your question correctly, but the problem is nobody bothered about solar storms because it didn't bother us before. And you can't really detect these storms without the sort of instruments that we have now. Yes, the aurora might increase, but that's about it. So if you lived fairly south, you wouldn't even know the effects. Valerie?
What are some potential mitigation strategies for these solar storms?
So people are looking to see how to safeguard the electrical grid, because it's a question of short-term inconvenience versus long-term inconvenience. So there, people are looking at steps and how the whole grid could be shut down for a short time to let the effects of the solar storm pass. Because the loading of wires is a problem only because they can burn the transformers. Transformers are expensive, difficult to build, difficult to replace. So you want to switch off the transformers and not let any of the extra electricity burn them. That's one of the ideas, for example.
Thank you.
Tina?
I'm wondering, like the other day we had the solar storm that came through, this whatever it was, the flare that came through and disrupted internet a little bit. How often does that happen, and how often is it worse?
How often it happens depends on where you are in the solar cycle. If you're towards the maximum, it can happen quite often. So let's go back to that graph. Such an event increases and decreases with the solar cycle, and we are actually pretty low on solar activity right now. So you can only expect these to increase the effects. How bad can they be? Again, that's a question we cannot answer, but it also depends on the direction of the magnetic fields they're carrying. The 2003 the Halloween storm, did not do as much damage as it could have done because the magnetic field of the wind was in the same direction as that of the Earth's magnetic field. So it buffeted it, but we didn't have all these, interactions between, remember, unlike magnetic fields attract, and they can interact and produce a lot of energy, which could have been a lot more destructive. That, again, we don't know till we measure it.
So if that same solar flare had happened at the top of the cycle, would it have been a worse occurrence, or would it?
No, not necessarily, no, because you can have very strong explosions even at the minimum. Yeah, that's a problem. Yeah. Charlotte.
So how do solar storms affect solar power? So if you have solar panels on your home, how would a solar storm impact?
It shouldn't. No, there shouldn't be any effect on that, no.
Okay.
Because it's not changing the amount of sunlight you're getting. Yeah.
So if the electrical grid is impacted, then if you're receiving...
Then it would be a problem. But if you're just talking about would your solar panels suddenly work more or work less, no.
Cool.
Yeah. Ricky?
Oh, forgive me. Can you hear me?
Yes.
I'm having computer problems. I found this absolutely fascinating.
Thank you.
And I'm so pleased that you increased my knowledge, although I am somewhat limited in what I can understand, but it was absolutely fascinating. A couple of things stood out for me. One, in response to an earlier question, and I forget, I think it was Tara who mentioned something about ancient civil. It brought to mind the tribe in Africa, the Dogon. The Dogon achieved notoriety because they could track the movement of a particular tiny star that astronomers had not seen before, even with their technological instruments. So that came to mind. I appreciated your response, and your response was, this is designed to help us support and maintain life as we know it.
Exactly.
There is the question of whether or not we should be thinking about other ways of doing things. But I do appreciate your insight about that. This is to maintain the technological system that we have going.
Yes.
There might
so
maybe
a tribe in the Amazon will probably not be affected by this at all.
Exactly. And we can probably not incorporate their knowledge at all.
Yeah, because you're right, because see, these solar effects, I mean, they have been going on throughout the history of the Earth. And yes, sometimes they're worse when the Earth's magnetic field gets weaker, because the Earth's magnetic field also has a cycle in some sense, not quite like the sun. But astronomy is such an old field, and yet these solar effects were first really recorded. I mean, by solar effects, I mean these big explosions, the effects on technology weren't recorded till about maybe say give or take 200 years ago. And it only made the news because of its effect on technology, because otherwise it's just a flash in the sun. The astronomers would have been interested because it's a flash in the sun, but who cares?
Yeah, it's interesting also that you mentioned Galileo.
Yeah.
Galileo was declared a heretic by the church because of his scientific inquiries and his scientific findings. I very much appreciated your presentation. Thank you.
Thank you very much.